Hello, hello. Hello everyone. So, today we'll start our next tutorial class, second tutorial class for the course of Fundamental of Statistical Thermodynamics. So, before starting today's class, let me discuss briefly about the things that we have done in the previous class. So, previous class, what we have discussed, let me just give me a brief recap. So, we have started our discussion about what do you mean by a weight of a configuration. Okay, so it's like if you have n numbers of particles, and if you distribute this particle, let's suppose in different box, each boxes let's suppose has n0 number of particles, n1 number of particles, n2 number of particles, like that. In that way, if you distribute total n number of particles, classical particles, which are distinguishable particles basically, so number of this type of arrangements you can it is possible, that is given by the weight of the distribution. Okay, number of possible arrangement of n particles. Okay, and that number of that possible arrangement W is basically given by this formula: n factorial by n0 factorial, n1 factorial, n2 factorial, like that. Okay, so as a practical example, let's suppose you have 20 balls or 20 particles. If you distribute those particles like this, like different box, like first box let's suppose is 1 particle, second box has 0 particles, third box has 3 particles, fourth box has 5 particles, next box has 10, and last box has 1 particle. So in this way, if you distribute this 20 particles, so now so the different ways, different possible arrangement you can do uh, for this particular configuration is that W is equal to 20 factorial divided by 1 factorial, 0 factorial, 3 factorial, 5 factorial, 10 factorial, and 1 factorial. This number is basically given by a very huge number, 9.31 into 10 to the power 8. So this is the weight of this particular configuration. Okay, next we have discussed some problems regarding this regarding this related to this weight of the configuration. Okay, so next we have discussed is that what is the possible, so there are many distribution is there, right, which can basically consistent with this particular configuration. So okay, so which distribution is highly preferred? Okay, which is the maximum preferable distribution with this particular configuration? Okay, so to calculate that maximal distribution, what we have done is that we first take the weightage, we take the ln, because since it's W is a very huge number, so it's easier to deal with the logarithmic of that particular number. So we take ln on both sides. Then our primary goal was to uh, basically take the derivative of this ln thing, and to find out for which distribution or which particular arrangement this ln of w gets maximized. Okay, so we know that the condition for which the function get maximized is that the derivative of that particular function has to be 0. Okay, this is the condition for extremum condition for any function. Okay, and it's true for here also, and here there are also two constraints we have to take. The first constraint was the total number of particles is conserved, so Ni is constant, summation over Ni is constant, and also the energy is also constant. So let's suppose E1 energy level as N1 particle, E2 energy level as N2 particle, so like that Ni into Ei would be total energy E, that is also constant. Okay, so these two are basically constraint that is related with this particular condition. Okay, particular extremum condition. Okay, so so that means if you want to maximize this thing uh, with addition of these two constraint, what you have to do is basically you have to use this technique called Lagrange method of undetermined multiplier. Okay, so then the equation become like this: delta of ln w into delta n plus alpha minus beta ei equal to 0. Okay, so if you apply this Lagrange method of undetermined multiplier, the condition becomes like this, and from there what you have to do, the first thing when you use this method, the first thing that you have to calculate is the what is the value of these two undetermined multiplier, that is alpha and beta. Okay, so we have calculated the alpha and beta. So the e to the power alpha term, we get it as 1 by summation over j e to the power minus beta ej. So this is basically the expression of alpha that you get, and the expression of beta is 1 by kBT. This is the inverse of temperature. Okay, so these two things we get, and after that, after substituting these two values of multiplier, we get the distribution like this: Ni by n. The distribution that is basically the reason for which the weightage will get maximized, that is this distribution. So beta ei by summation over j e to the power minus beta ej. This is the distribution known as the Boltzmann distribution. So this distribution is the the particles tends to in thermal equilibrium, in a thermal equilibrium system, so particle tends to distributed among the energy level by obeying this particular distribution. Okay, so basically that means that the distribution of each, so what does this physically means is that if you see the expression, so the distribution of particles in each ith energy level is basically associated with the energy value, the ei, with that particular energy level. Okay, so if the energy levels are like this, let's suppose this is E1, this is E2, this is E3. So let's suppose the number of particles, there's total number of particles, let's suppose is n. Okay, that are distributed throughout this energy level, and out of this n particle, how many particles are there in the E3 energy state, that will be given by n3 equal to n3 by n. This is a fraction of particles that are in the energy state E3, will be n3 by n equal to e to the power minus beta E3 divided by summation over e to the power all ei basically. Okay, so this is how we can calculate the distribution of particles in each energy level. Okay, by using this Boltzmann distribution, and this particular quantity that is in the denominator of this distribution, this is a very important quantity that you face again and again in thermodynamics or statistics, especially in statistical mechanics, and this thing is known as the partition function of the system. Okay, so this thing we are basically denoting it as Q. So q is basically summation over j e to the power minus beta ej. So this is known as the partition function. Okay, so before dealing any kind of problem related to statistical mechanics, if it's possible, then always first calculate the partition function of the system, and using that you can basically calculate in the later tutorial also you will see that using this partition function you can basically calculate any equilibrium thermodynamic quantity of that particular system. Okay, next we have discussed the what is the basically behavior of this particular partition function at different temperature scales. Okay, so yeah, also there is one another thing. So each energy level can also have degeneracy. Okay, so we, by considering the degeneracy also, you can write the partition function like this, e to the power j qj. So degeneracy we are denoting as gj. Let's suppose ej energy level has degeneracy gj. So then the partition function expression will be looking like this, gj into e to the power beta ej. Okay, now we have discussed that when the temperature is 0, temperature tends to 0, the partition function will be equal to tends to g0. Okay, and we also saw that is that the particles, uh, the number of particles at the ground state would be equal to n. Okay, so n0 by n will be equal to 1, right? So that means what happens is that if you basically if you make the system temperature close to the absolute value, in that case all the molecule inside the system will tends to move towards the ground state of the system. Okay, so this thing will happen at 0 temperature, and at t tends to infinite, what happens is that q, the q will be basically summation of g0 plus g1 plus g2 like that. So the basically addition of the degeneracy associated with each of the energy level, and in that case we also saw that the n0 by n will be equal to, sorry, n1 by n will be equal to n2 by n equal to n3 by n. So that means each of the energy levels has a equal probability of getting uh, equal probability distribution. Okay, so that means the number of particles distributed in each of the energy levels will be equal. Okay, so that what will happen if you take the temperature very high, close to infinite. Okay, and we also saw the same phenomena or behavior of the system by showing some of the examples also. Okay, so these are the pretty much the things that we have discussed in the last class. So now for today's class we'll start something related to this only. Okay, not that much different. So yeah, so first we'll start our discussion about the molecular partition function of a uniform ladder of energy levels. Okay, so this was our expression. Let me write it as big 2. So this was the expression that we have in our hand. So q, the partition function will be summation over j gz e to the power beta ez. Okay, now so now the our main goal will be, first is the molecular partition function of a uniform ladder of energy levels. Okay, so what does that mean? That means is that so basically the energy levels are distributed like this. This is the zeroth energy level with energy 0. This is the energy level E. This is 2E. This is 3E, and like this only. Okay, so this is a definition of a example of, you can say, example of a uniform ladder of energy. So uniform means is that the difference between energy or between two successive levels would be equal. Okay, so here this difference is basically E. Okay, so this difference is equal for all of the energy levels, I mean difference between all of the energy levels. So okay, so yeah, so now for this kind of a system, this kind of a uniform energy ladder type of a system, you can calculate the total partition function easily. Okay, so how you do that? First, right, so let's suppose for the time being that we will not consider the degeneracy. Let's suppose the degeneracy is 1 for every energy level. Okay, so in that case q would be summation over j e to the power beta ej. So now you can write it like this: q equal to e to the power minus beta into 0. Just take the summation and discretize the summation basically. So 1 plus e to the power beta e plus e to the power beta 2e plus e to the power beta 3e, and like that. Next can write it, so 0 beta, so e to the power 0, so it will become basically 1 plus e to the power beta e. Next plus e to the power minus beta e, this will be, you can write it as whole square. Next is e to the power beta e whole cube plus dot dot dot. So now now you can write now you can use the binomial formula, right? So let's suppose if you have some number like this 1 plus 1 plus x square plus x cube. Now this way, if you can write it as in a closed form, right? That is basically given by 1 minus x inverse. Okay, that we know. The condition, the given condition is mod of x should be less than 1. Okay, yeah. So in this case also, since is e to the power beta e is greater than 1, that means 1 by e to the power beta e should be less than 1. Okay, I mean it would be much less than 1. Okay, so this condition is true for here also. So that means we can use this binomial distribution formula here also. So 1 plus, so in that case the x would be basically, in our case the x would be basically e to the power minus beta e here, right? So now, so similar way, this whole thing you can write is like 1 minus e to the power minus beta e inverse. Okay, or q equal to 1 plus 1 by 1 minus e to the power minus beta e. Okay, so this is a very compact form. So for this system of uniform ladder of energy, so we can write the total partition function of this kind of a system in a very compact way. Okay, a very closed format. Okay, so this can be determined actually. Okay, since the series is convergent, that's the reason we actually can do this sum. If it has increasing values of degeneracy, then we cannot basically use this closed form actually. Okay, so the given condition is that each energy level has one degeneracy value of 1. Okay, now, so if you know the partition function, so by using that thing you can easily calculate now what is the probability distribution or the fraction of particle that is distributed in the ith energy level, right? So that expression is basically given by pi, we know that. So pi is basically ni by n that is e to the power beta ei by q, right? And here q is 1 by, so it would be 1, so q would be, yeah, it would be like this, e to the power minus beta ei into 1 minus e to the power minus beta e. Okay, yeah, so e is basically here the, yeah, e is the difference in the energy level. Okay, here difference in energy levels. Okay, so this is the formula of population in each of the energy level. Okay, for the case of an uniform ladder of energy. Okay, now we'll do some problems, some MCQ type of problems on this particular thing. Okay, so the first problem is system has partition function equal to q equal to 1 plus e to the power minus beta e divided by 1 minus e to the power minus beta e. So the question is the degeneracy of the ground state is, the options are option A 0, option B 1, option C 2, and option D infinite. Okay, so the four options are given. So here basically, so you have to do a back calculation here. So you have to write this whole thing. So this partition function you have to given here as a closed form. So from here you have to basically write it in a summation way, in terms of summation basically, so that from there you can easily get the value of the degeneracy of the ground state. Okay, so for that what we can do is that, so first let me write the q as 1 plus e to the power minus beta e divided by 1 minus e to the power minus beta e. So the denominator term we can write it like this. So since we know e to the power minus beta e is less than 1, right? So that means we can basically write this denominator as a series, binomial series, right? Just like we did in the previous discussion. So so we can write it like this. Let's suppose for the sake of calculation, let's take e to the power minus beta I for x. Okay, so write it as 1 plus x into 1 minus x inverse. So now I can write it like this, 1 plus x into, so if you extend this series, it looks like this, 1 plus x square plus dot dot dot. Now if you multiply this thing with this thing, you will get q as 1 plus 2x plus 2x square plus 2x cube plus dot dot dot. Now the substitute, q would be 1 plus 2 into e to the power beta e plus 2 into e to the power minus 2 beta e plus 2 into e to the power minus 3 beta e. So like this. So you can see these are, so we know our general expression of q is this basically, g0 plus g1 e to the power minus beta e1 plus g2 e to the power minus beta e2, also like this. So why do you know g0 is basically uh, the what is degeneracy of the ground state. So if you compare this equation 2 with equation 1, you can easily get the g0 value for the problem that's given, for the given problem is g0 is basically equal to 1, right? So that means the ground state degeneracy is basically equal to 1. So similarly, if in the problem if it's mentioned that what is the degeneracy of the first excited state, and here you can easily see by comparing the g1 is basically here is 2, right? So in the problem it's mentioned if you are supposed to find out the degeneracy of the first excited state. In that case the g1 should be equal to 2. Okay, so here in this problem the g0 is, so the correct answer would be option B. Okay, the next problem. System has energy levels En equal to Ne and Gn equal to 2n plus 1. So in the problem it's mentioned that each energy level has energy Ne. So let me see, one has E, E2 has 2E, E3 has 3, so like that. So that means here also the problem is a uniform ladder problem, and the difference is that here we have degeneracy that is associated with each energy level. So degeneracy basically increase as 2n, as in 2n plus 1. Okay, so n is basically the state of like the level of the energy, nth level of the energy. So the question is that find the partition function. Okay, so the option A is 1 by 1 minus x, option B is 1 plus x divided by 1 minus x whole square, option C is 1 by 1 minus x whole square, and option D is 1 by 1 minus x whole cube. Okay, okay, so yeah, so these are the 4 options given. So the first thing is that first you would use the expression of the partition function that we know here. So q is, we know, is summation over gj into e to the power beta ez, right? So here it would be like this. So for the sake of calculation, let's take e to the power beta e as x. So e to the power minus beta e as x. So that means e to the power minus 2 beta e would be x square, e to the power 3 beta e minus 3 beta will be x cube, and like that only. So here it would be, so gj will be 2. So the what is the degeneracy is 2n plus 1, and this thing will be, we can write it as x to the power n. Okay, since we know the energy is basically scale up with n, n into e basically, so x to the power n. So the summation is will be over n equal to 0 to infinite. Okay. Yeah, so that means the partition function q is basically 2 into summation over n x to the power n plus summation over n into x to the power n into x to the power n and x to the power n, right? So as you can see, there are two summations are there. Okay, so the second summation is easy, right? So second summation is the normally the formula that we know, the formula of the binomial expansion, right? That is that we know 1 plus x square plus x cube dot 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 would be basically 1 by 1 minus x. Okay, so that means this thing has a closed form, that is 1 by 1 minus x. Now next you have to evaluate this thing. Okay, so how do you do that? So this thing is actually also have a closed form, the closed form of the summation. This summation basically converges to a very closed form. So that form we need to know in order to get the expression that are given in the options. Okay, so how to do that? So there is a way to basically find out that form of the summation. So first let me write out this thing, 1 by 1 minus x we know is basically this thing, 1 plus x square plus x cube, like this. Now if you take, so this is nothing but the summation over x to the power n, right? 1 minus x inverse. Okay, so now from here, if you take the derivative on both the sides of this side, so d dx of 1 minus x inverse equal to summation over d dx of x to the power n. Okay, summation is over n. So now after doing the derivative, you will get this side as 1 by 1 minus x square equal to, take the derivative of x to the power n, it will give you summation over n into x to the power n minus 1. Now if you multiply x on both the sides, it will give you x into 1 minus x whole square equal to summation over n into x to the power n. Okay, as you can see, this is the thing that we want to find out here, right? What is the summation of, what is the closed form of this summation that we got? That is nothing but x divided by 1 minus x whole square. Okay, okay, so we basically got the closed form of both these two summation. Now we have to substitute those two things here. So now let me do that. So let me rewrite it once again. So what was q? Q was 2 into summation over n x to the power n plus summation over x to the power n. So the first summation gives you x into 1 minus x whole square, and second summation gives you 1 by 1 minus x. Okay, now just do the algebra. Okay, so it will give you, just add these two things. So this will give you 1 minus x whole square 2x plus 1 minus x. So this will give you 1 plus x divided by 1 minus x whole square. Now so since x is nothing but e to the power minus beta I, so just substitute that thing here. So you will get 1 plus e to the power minus beta e divided by 1 minus e to the power minus beta e whole square, right? So this would be our correct, this would be our result. Okay, so this matches with the, yeah, so this matches with the basically this one, option B. Okay, so this is easy. So just you have to start with the definition of the partition function, the general definition of partition function, and from there we have to use this formula of these two series, the closed form of these two series, n into x to the power n and x to the power n. So the second one we already knew, we have used it previously. The first one you can either remember it or you can calculate it, whatever way. So from there you can easily get the formula, but by substituting those two closed form, you will get the answer. That is basically the expression of the total partition function. Okay. Okay. So this problem is done. Okay. So next we will be discussing the problem number 2. Sorry, problem number 3. So problem number 3 is calculate the proportion of CO. CO is the molecule name. CO molecules in the ground state, first excited state, and second excited state. Okay, at temperature T is basically 298 Kelvin, and the vibrational wave number is given by nu tilde is 2170 centimeter inverse. Okay, yeah, so basically here these are basically the vibrational energy levels. Okay, so the thing is that, so the molecules can have different types of vibrational energy levels. Okay, so each of the vibrational energy level has energy En, basically has n into hc nu tilde. Okay, where n is the number of the energy level, and hc nu tilde, okay, that is basically a kind of a constant value for a particular spectra, vibrational spectra. Okay, so it's like this. So these, let's suppose, are the energy levels. So this is basically E1 has equal to hc nu tilde, E2 has 2hc nu tilde, E3 has 3hc nu tilde. Okay, as you can see, So each energy levels are basically as in basically integer multiple of Hc new tilde. Okay, and the difference of energy between each of the energy levels are basically Hc new tilde. So we can consider this kind of a system, vibrational energy systems of a molecule as a uniform ladder, right? Uniform energy ladder levels. So our main thing that we need to calculate is the calculate of proportion of CO molecules in the three states: ground state, first and second excited state. So to calculate that thing, we know first thing that we need to calculate is the partition function. Okay, so the partition function, the formula you already know, right? This was the formula for the partition function of uniform energy ladder. Uh, this is the formula, right? This is the formula. So, and this was the formula distribution of the number of particles for the case of uniform ladder. For that also there is a formula which is given by this. So we have to use both of these two formulas to get the answers. Okay, so let's start. So first thing that we know is the partition function is expression looks like this: 1 by 1 minus e to the power minus beta. So here the energy levels are Hc nu tilde, so it will be to the power minus beta. Here E is basically Hc nu tilde, right? So the first thing that we have to calculate is the value of this E. So here E is Hc nu tilde. So H value is known, the Planck constant. So let write everything as SI unit. So 6.626 into 10 to the power minus 34 joule per second, right? Next is the speed of light, 3 into 10 to the power 8 meter per second. And nu tilde is the wave number. Okay, so wave number here is given as 2170 centimeter inverse. So if you convert it into the meter inverse, you have to multiply it with 100, right? 100 meter inverse. Okay, so if you do that, do this multiplication, you get the E as the energy difference between basically each of the levels. E is as 4.311 into 10 to the power minus 20 joule. Okay, so since you got this, the next thing that we need is the beta. Beta, the temperature is given here, that is 298 Kelvin. So beta is given by 1 by kBT. So equal to, the kB is the Boltzmann constant, right? So that value is 1.38 into 10 to the power minus 23 into 298. So that gives you the value of beta as 2.43 into 10 to the power 20 joule inverse. Okay, so we got pretty much all the numerical quantities that needs to be done for this for the sake of calculation of this problem. Okay, so now we have to substitute all of this thing here into the expression of Q. So Q would be equal to 1 by 1 minus e to the power minus, so 2.43 into 10 to the power 20 into 4.311 into 10 to the power minus 20. So if you multiply this whole thing, it will give you 1 by 1 minus e to the power minus 10.48. Okay, so e to the power minus 10.48, if you do the calculation, it will give you 1 minus 2.8 into 10 to the power minus 5. So this is nothing but 1.000028. Okay, so it's very close to 1. Okay, yeah, so we got the expression of the Q, the partition function. And the problem is, first thing that you have to calculate is the the distribution or the fraction of molecules in the ground state. Okay, so that is P0 basically. P0 is basically N0 by N, that is the 1 minus e to the power minus beta e into 1 minus beta into 0, right? So it will be 1 minus e to the power minus 10.48 into 1. So this will give you 0.999972, the P0 value. So as you can see, for this particular temperature T equal to 298 Kelvin, most of the molecules are basically in the ground state. Okay. You can see N0 is 0.999972 into N. So that means almost 99% of the molecules are in the ground state of the system. Okay, for this particular temperature. So let's see what happens in the first excited state. Okay, so the first excited state is P1 is basically 1 minus e to the power minus same beta e, so that would be 10 to the power minus 0.48 into e to the power minus beta e, so that would be also 10 to the power minus 48 into the 10 to, e to the power minus 10.48. So it will give you, if you calculate it, it will roughly give you 2.8 into 10 to the power minus 5. So as you can see, this very less fraction of molecules are there in the first excited state. The order of the fraction of 10 to the power minus 5 order. Okay, so this is very less. And if you go to further, the second excited state would be further less. So P2 would be 1 minus e to the power minus 10.48 and to the power minus 10.48 square. So beta e, 2 beta e, so we have 2 beta e square, we can write it like this. So it will give you roughly around 7.8 into 10 to the power minus 10. As you can see, it's further very much smaller. Okay, so this is the way you can calculate for a real system. For a real system where for what you can easily calculate the distribution of particle in each of the energy levels. Okay, using this formula that is for the uniform energy ladders. Okay, so next problem is similar type of problem. Find the fraction of HCl molecules in the vibrational states nu equal to 0, equal to 1, equal to 2 at 500 Kelvin. Okay, given nu tilde equal to 2885 centimeter inverse. Okay, so similar way, similar formula also have to use here. So first thing is the difference in energy level, that is E, that has to be first calculated. So E is basically Hc nu tilde, right? So H we know is 6.626 into 10 to the power minus 34. Same all the things. Light is all the quantities are writing in SI. 10 to the power 8. The nu tilde is here now, 2885 in meters inverse into 100. So if you do that, the energy roughly will get, energy difference roughly will get as 5.72 into 10 to the power minus 20 joule. Okay. Next is the beta, 1 by kBT. So T is here at 500 Kelvin. kV we know is 1.38 into 10 to the power minus 23. So if you do the calculation, you'll get beta as roughly around 1.45 into 10 to the power minus, 10 to the power plus 20 joule. Okay, so you got this. Now the next thing is you need to calculate the Q, the total partition function. Since it is also energy ladder, so you'll just use that form that you have derived. So Q would be 1 minus e to the power minus beta E. That would be, if you calculate it, between 1 minus 1 by e to the power minus beta is 1.45 into 10 to the power 20 into 5.72 into 10 to the minus 20. If you do that, you'll get roughly the Q as 1.00025. Okay, pretty much close to 1 that we get in the previous problem also. So here also similar way, just calculate the probability at to be in energy 0 is ground state is P0 equal to 1 minus e to the power minus beta E. Yeah, that would be equal to 0.99975. P1 would equal to 1 minus e to the power minus beta E into e to the power minus beta E. That would be equal to 2.5 into 10 to the power minus 4. Lastly, P2 is 1 minus e to the power beta E into e to the power minus beta E, 2 beta E, so you can write it as a whole square. So e to the power beta E, you have know the value, so if you substitute it, you will get around, roughly around 4.6 into 10 to the power minus 8. These are the type by which the molecules will be distributed in each of the energy levels: ground state, first excited states, and the second excited states. Okay, so far you can see, since the temperature is not that much high, so what we observed is that most of the molecules are basically distributed in the ground states. There is very less fractions that are available in the higher excited states. So now let's take a problem where we will consider a bit higher temperature. Okay, so the problem number will be 3 for NO with vibrational wave number nu tilde is equal to 1904 centimeter inverse. Calculate the proportion in equal to 0, 1 and 2 at 1000 Kelvin temperature. Okay, so similar problem, but here I can see the temperature will be a bit higher, 100 Kelvin or 1000 Kelvin. So we'll check how this temperature plays a minor role in order to basically regulate how the particles are distributed in the energy levels. Okay, so here also first thing we have to calculate is the energy level. So here, since it's a saying the vibrational wave numbers, so vibrational energy states are associated with this problem also. So the first thing that you have to calculate is the energy levels difference, that is E, which is hc nu tilde. So Similar way, so here 1.38 into 10 to the power, sorry, 6.626 into 10 to the minus 34 into 3 into 10 to the power 8 into neutralizing 1904 into 100 meter inverse. So all of them are in SI. So it will give you E as 3.79 into 10 to the power minus 20 joule. This is the E. The second thing is needs to be calculated is beta. That is the 1 by kVt. Okay, so here T is higher, 1000 Kelvin. So if you calculate it 1.38 into 10 to the power minus 23 into 1000 Kelvin, it will give you roughly 7.24 into 10 to the power 19 joule inverse. Okay, so got these two main quantities, and yeah, so now the next thing that we need to calculate is the total partition function. Since the total partition function is from using the expression for uniform energy ladder level, so 1 minus e to the power minus beta e, so 1 by 1 minus e to the power minus beta, so it will give you 7.24 into 10 to the power 19 into 3.79 into 10 to the power minus 20. So if you do this multiplication, you will get 1 by 1 minus e to the power 2.74. Okay, minus 2.74. So yeah, so this roughly gives you equal to 1.067. This is the value of Q here. So so from that, first we'll calculate the population that is in the ground state energy. So that is nothing but P0, right? P0 is 1 minus e to the power minus beta e, so 1 minus e to the power minus 2.74, that roughly gives you 0.935. okay, so as you can see, it's not like the earlier problems where we mostly observe the 99% of the molecules are in the ground state. So here you can see there is a noticeable improvement. So 93% of the molecules are in the ground state. The rest around 6% are in the excited states. Okay, so this happens because of the high temperature. So here you consider comparatively higher temperature equal to 1000 Kelvin. So because of that, many particles are also distributed in the higher excited states. Okay, so that we will also see. So P1 has 1 minus e to the power minus beta e into e to the power minus beta e. So it will give you 1 minus e to the power minus 2.74 into e to the power minus 2.74. So if you calculate this, it will give you 0.063%. Okay, so that means around 6%, 6.3% particles are still distributed is in the first excited state, and this value, the numerical value, is quite higher than the previous two cases where you get the population fraction is almost around the order of 10 to the power 4 or 10 to the power 5. Compared to that, here we see a significant amount of particles are there in the first excited states, right? The similar way, second excited state, if you see, P2 is 1 minus e to the power minus beta e into e to the power minus 2 beta e. So it will give you 1 minus e to the power minus 2.74 into e to the power minus 2.74 whole square, which is roughly around 0.0042. Okay, so around 0.4% are there distributed in the second excited state. Okay, so as you basically moves on higher and higher excited states, so the percentage will become smaller and smaller, obviously. So yeah, so these are the way you can calculate the fractions for real system if you know the know the basically the spectra, the wave number of that spectra that is coming from the vibration energy levels, and if you know the temperature, so from there you can basically calculate which vibrational spectra has how many fractions of total molecules. Okay, and that also we see for different the temperature plays a very major role in order to decide these fractions. Yeah, so next thing that we'll calculate is first we'll discuss the partition function of a particle that is moving in a 1D box. Okay, so in quantum mechanics you already done. Okay, so what is the energy for a particle if it's moving in a 1D box? So by using the results that we learned from the quantum mechanics, basically results means here I am denoting the energy levels. By using that thing, we'll formulate the partition function for a similar system where the particles is trapped inside an infinite potential well. Okay, so that we'll do now. So let me write it. Partition function of a particle moving in a 1D container. Okay, so initially we'll consider 1D container, then we will generalize from that expression, we'll generalize this expression for the 3D case. Okay, so 1D container of box length x. Okay, so from quantum mechanics we know that we have solved that if you trapped a particle inside the infinite potential well, and for that kind of a system, if you solve the Schrodinger equation, you will find out that these particles can have this quantum of energy, quanta of energy. Okay, so the energy states are basically discretized. Okay, so like this: n equal to 1, n equal to 2, n equal to 3. So the particles inside a potential well can have these discretized states of energy, right? And the energy values basically given by En equal to n square h square by 2, sorry, 8 m x square. Okay, so basically m is the mass of the particle here, and x is the length of the box. Okay, that is this thing, x box. Okay, so by knowing these two quantities, by using the Schrodinger equation in quantum mechanics, we have get this particular expression of energy, right? So as you can see, so each energy levels each energy levels has this multiple square multiple of h square by 8mx square. So okay, so the lowest energy of the lowest state would be n equal to 1, lowest energy level is basically given by h square. So E1 is basically h square 8mx square, okay, which is basically E. Now, as you can see, in the case of uniform energy ladder case, we started the ground state energy. If you see here, we started the ground state energy has with energy equal to 0 here. Okay, but here in this case, for the case of when the particle is trapped inside a quantum well, infinite well, in that case, the ground state energy is not 0. It has a particular value which is given by this. So now to make this whole system to make it as a uniform energy ladder, what you can do is that we can subtract each of the energy level by this ground state energy level. So by doing that, we basically scaling down the values of each energy levels. So the reason for doing that is that the ground state energy in that case, the lowest energy level in that case will also become 0. Okay, so we will subtract each of the energy level by using this lowest energy level, and if you do that, the ground state energy will become 0 now. Okay, so like this ground state energy will become now 0. First state energy will now become uh, so the first state has n equal to 2, right? So it has 4h square by 8 mx square minus h square by 8 mx square, right? Similarly, the third would be 9 h square by 8 mx square minus h square by 8 mx square, right? So in this way, you basically subtract each of the energy level with the ground state level. So the in that case, the rewritten version of the nth energy level looks like this: n square minus 1 equal to h square by 8 mx square. And for our ease of using notation, we can write this whole thing as a constant e, so we can write it as n square minus 1 by e. So where e is this whole constant, h square by 8 mx square. Okay, now this n value can start from 1, 2 and dot dot dot. So 1 is for ground state, 2 is for first excited state, 3 is for second excited state. And as you can see, now it becomes a uniform ladder where the still it's not actually uniform ladder, because the although you have make it the ground state as 0, but still here the difference between the each energy level is not equal actually. Okay, so in that we cannot call it as uniform ladder, although it's an energy ladder, but it's not uniform still. So for that reason we have to use a different summation rule here. Okay, so The partition function, the expression would be summation over n e to the power minus beta en. So beta en, now it will become n into e to the power minus n square minus 1 into beta e. Okay, so now since we know for this quantum mechanical system this energy levels are very much close to each other and the number of energy levels are almost infinite, very high value I want to say. So because of that we can consider these energy levels are very not as a discretized level, but you can take it as a continuous levels. Okay, so, so we can, that means we can basically write the summation as a form of integration. Okay, so if you do the integration it will give you, so we'll write this thing. So since the translational, so these are all known as the translational energy. Okay, this translational energy levels are very close together in a container of size of L. Therefore the sum can be approximated by an integral. Okay, so this simplification we can do. So we can write this whole thing as an integration. So qx would be integration over 1 to infinite e to the power minus n square minus 1 beta e into dn. Since n is very high compared to 1, so we can approximate this thing as 0 to infinite e to the power n square beta e into dn. Okay, so if n is very high, in that case we can write this thing as integration. So integration, we will do the integration now. So this integration, so we have to use this Gaussian form of integration here. So for that we have to do some variable substitution. So first thing we will do, we will consider x square as n square beta e, and if you do the differentiate both sides, it will become 2x dx equal to 2n dn beta e. So dn will become x by n into 1 by beta e dx. Okay, now so x, so we have to write the whole thing in terms of x. Okay, so here the n thing we can write it as, so x square by n square is beta e, so x by n you can write it as beta e, so square root of beta e, substitute it here, so it will now become x by n will become beta e into root and square root of beta e into 1 by beta e into dx dn. Now so it will become 1 by square root of beta e into dx dn would be this thing. So now qx, okay, so now it will become, yeah, So now qx will become, so if you substitute this thing here, it will become 1 by root under beta e. You can take it as common, take it outside the integral, so 0 into 0 to infinite e to the power minus x squared dx. So we have changed the variable. Now this integration e to the 0 to infinite e to the power minus x square dx. So this is a very standard integration. So it has a fixed value, known value, which is root under pi by 2. Okay. So this result we will use here. This is a very standard result. So it will now become 1 by root under beta e into root pi by 2. It will give you pi by 4 beta e. Okay. So yeah. So now e, we know e we have taken as h square by 8 mx square. So we'll substitute it here. So we'll get now the full expression of this q. So qx, the translational partition function, will now become, if you substitute the expression of e here, it will now become pi 8 mx square divided by 4 beta a square. So it will become, so if you cancel the terms, common terms, it will become 2 pi m n pi beta h square to the power half divided by x. This is the basically the expression for the translational partition function for the case where the particles is trapped in a infinite potential well. Okay, a single particle. Basically, this is for single particles, and the dimension is 1d. So yeah, so we start from the results that we got from the Schrodinger equation, where the energy levels is discrete. This is expression for the discretized energies, and we then renormalize the energy such that the ground state energy becomes 0. So for that we have subtract each of the energy levels by the ground state energy levels. So after doing that, what we did is that we basically get this form of the energy level, renormalized energy levels, and from there we calculate the partition functions as a summation form. We have taken the summation form first, then we consider that the energy levels are very close to each other, so we consider this discretized energy level as continuous levels, and we take then change the summation as the integration, and we then use this variable can say change of variable method to do this integration basically, and from there we get a very closed form, a very known form of this expression of the translational partition function for this particle, which is given by this. Okay, and yeah, so as you can see, this translational partition function is basically doesn't depend. Okay, this partition function doesn't depends on so partition function doesn't depends on the length of the box, okay, or the container, whatever it is, length of the box that we have taken as x in our system. So it doesn't depend on that particular length of x, and it depends on only the mass and the temperature. Okay, depends on mass m and t. Okay, so these are so we got a very useful insight of the things that decides the partition function for the particle. If this is in 2D, for case of 3D, we can extend the same extend this this already established result here also for the case of 3D. Yeah, so so in quantum mechanics also we know the in case of a 3D box, so the energies one looks like this, right? Basically nx squared by n squared by 8 pi x squared and y squared by h squared into 8 pi y squared and then z squared by h squared by 8 pi z squared, right? So basically, so if this is suppose the box looks like this, a 3D box, okay. So like each axis, this is the x-axis with x, y-axis is y, and z-axis as z, okay. The length of each of the axis, okay. So in that case, the energies looks like this, discrete energy level looks like this, that is a known result from quantum mechanics, right? So that means you have contribution of energy as a added form for each of the dimensions. So E nx as x, E ny as y, plus E nz as z. This is the total energy. Now from here, the same way you can calculate the for all the 3 dimension, you can calculate the partition function, right? B into E nx minus B E ny minus B E nz. Summation would be over all n, okay. I mean nx, ny, and z. If you take the sum, you can write this whole thing as a multiplication, right? So it would be summation over nx into e to the power minus beta e nx, summation over ni e to the power minus beta e ny into summation over uh, nz e to the power minus beta e nz, okay. So q, the 3D partition function q is basically the multiplication of the partition function of x, y, and z axis, right? So qx into qy into qz, okay. So if you calculate the partition function along each of the direction qx, qy, and qz, and then multiply them, we'll get the partition function for the case of a 3D system, right? So for the qx, for one dimension you already knew the expression, right? So qx is 2 pi m by h square beta half into x. Q y is similar way 2 pi m by h square beta half into y, and qz is 2 pi m into h square beta to the power half into z. So now these three quantities you can independently calculate, right? Just the way we have done in the previous derivation. So just substitute all of them here into the expression of the q. So q would be in that case multiply these three things, 2 pi m into h square by beta to the power 3 by 2 x y z, right? Now what we can do is that we can take the multiplicity. XYZ is the basically the sides of the box, right? X-axis along x-axis, y-axis and z-axis. So XYZ basically gives the V, that is the volume of the box, right? So if you got the volume of the box, then we can write this function as a more simpler form. So Q would be, we can write this thing 2 pi m by 2 pi m at by, so we write this thing called the thermal wavelength of lambda. So lambda definition, we are taking it as h square beta by 2 pi m to the power half. So if you calculate this, the dimension of this particular quantity, you will see this is dimension of length. Okay. So that's why we are calling this thing as lambda, which is known as the thermal wavelength. Okay. Of any particle, you can calculate this thing for any particle actually, thermal wavelength. Okay. So this thing you can write it as, so if you write in terms of lambda and v, it will become v by lambda q. Okay, partition function v. But lambda, you can rewrite lambda like this also, h by 2 pi m kbt. Okay, this is also a valid expression of lambda. Okay, so if you do the lambda of the particular system, you can calculate the partition function for 2D, for 3D, for 1D. Okay, and you also need the volume of that particular container or box, is also you need to calculate the Q. Okay, so next we'll do some problem on this. Okay. Okay, so the first problem is problem 1. Uh, Nitrogen molecule of molar mass 28 gram per mole is confined to a cubic container of volume V equal to 1.5 into 10 to the power minus 3 meter cube. Calculate the translational partition function at A T1 equal to 250 Kelvin and B T2 equal to 500 Kelvin. Okay. Then compute the ratio Q of T2 by Q of T1. Okay. So the nitrogen molecule is trapped, the molar mass is given, the volume is given, temperature is also given. So the most of the thing that is needed to calculate this partition function is already given in the problem. So for the case of 2 temperature, we have to first calculate and we have to take the ratio. Okay. Okay, so this is in 3D, right? So yeah, 3D. You have to use the formula for 3D. Hmm. Okay. So first you have to calculate the mass. Okay. So mass of a single nitrogen molecule. Okay. Because we know this is the formula of the translational partition function, and so Q is V by lambda Q, right? So the expression is V into 2 pi m kBT by A square to the power 3 by 2. This is the expression of Q. So Q translational basically. So we need the first expression of mass. So here for 28 gram per mole, so 1 mole has 28 grams. So that means the mass of N2 would be 28 into 10 to the power minus 3. So we write in kg, so 10 to the power minus 3 kg by 6.023 into 10 to the power 23. This will give you the mass of each N2 in terms of kg, so it will be around 4.65 into 10 to the power minus 26 kg. So now from here, so we will now calculate the translational partition function. So first we will calculate this thing only. Okay, we will not take the temperature right now. Okay, so 2 pi m k by square. Okay, 2 pi m k, sorry, 2 pi m k by a square to the power 3 by 2. Next we will multiply this thing, this constant thing, with the two different temperature, and by doing that we will get the two different partition function values. So first is that 2 pi, we get 2.3.14 into and we know 4.65 into 10 to the power minus 26 kg. Boltzmann constant 1.38 into 10 to the power minus 23. The whole thing is divided by the square of Planck constant 6.626 into 10 to the power minus 34 whole square. Okay. If you calculate this thing, it will give you, so the numerator give you around 4.03 into 10 to the power minus 48. Denominator give you 4.39 into 10 to the power minus 67. So the whole thing to the power 3 by 2, 3 by 2. So if you divided this will give you approximately 9.18 into 10 to the power 18 to the power 18 by 3 by 2, and that is roughly around 8.8 into 10 to the power 27. Okay, so this is the value of this particular constant. Okay, now so for two different temperature we have to calculate. So the first temperature we'll do for T equal to 250 Kelvin. Okay, so for T equal to 250 Kelvin, if you do that, so Q trans would be V into 2 pi m kT by a square to the power 3 by 2, right? So we know the V is 1.5 into 10 to the power minus 3 meter in meter cube. So 1.5 into 10 to the power minus 3 is 2 pi nk by square to the power 3 by 2. That thing I've calculated already. That expression is 8.8 into 10 to the power 27, and here t to the power 3 by 2 is there only. So t to the here t is basically 250 Kelvin, right? So 250 to the power 3 by 2, if you do, it will give you roughly around 3952.5. Okay, that means Q trans would be 1.5 into 10 to the power minus 3 into 8.8 into 10 to the power 27 into 3952 into 0.5. Now if you do this calculation, you will get Q translation around 5.22 into 10 to the power 28. So this is the expression of the translational partition function at 250 Kelvin. Now next we will calculate for 500 Kelvin. Okay, so T equal to 500 Kelvin. So T will be equal to 500 Kelvin. To calculate 500 Kelvin the similar way, so Q translational will be 1.5 into 10 to the minus 3. These quantities will be similar. The only thing that is the temperature that will get changed into. So 500 to the power 3 by 2. Okay. Now if you do this calculation, it will roughly give you around 1.48 into 10 to the power 29. So as you can see, there is an order of 10 difference is there. Okay, so between the temperature at 500 and at 400 Kelvin. Okay, yeah. So this is the way you can calculate. So using this translational partition function for a particle, if it's confined in a cubic container. Okay, so different temperature you will get different, obviously different values of this translational partition function. Okay, so next problem is calculate the translational partition function of a helium atom confined in a volume of 200 cc at T equal to 298 Kelvin. Okay. Okay. So here the mass and all are given. So mass is given as 4 point, sorry, 1.6605 into 10 to the power minus 27 kg. The KBT temperature is given equal to 4.116 into 10 to the power minus 21 joules. Planck constant H is given 6.626 into 10 to the power minus 34 joules. These are the quantities that are mentioned into the problem. So on the basis of that, so first we calculate the first thing, that is the Broglie wavelength. Okay, this is the first and foremost thing that we have to calculate, right? So answer is first is the lambda, that is h by root under 2 pi m kBt. Okay, so h is 6.626 into 10 to the power minus 34 divided by 2 pi into 6.646 into 10 to the minus 27 into 4.116 into 10 to the power minus 21. Okay, so now if you calculate the lambda here from the given information, you will get around 6.91 into 10 to the power minus 11, that is meter. That is the value of thermal wavelength lambda, and the volume is given as V is 200 centimeter cube. Now since you are everything is using we are writing using the SI unit, so we have to convert it into meter. So it will become 2 into 10 to the power minus 4 meter cube. Okay. Okay, so now from here Q would be become V by lambda cube. So V is 2.2 into 10 to the power minus 4 divided by 6.91 into 10 to the power minus 11 cube. This will approximately gives you 6.05 into 10 to the power minus 26. Okay, so this is the value of the partition function Q for this system. Okay, so next is the last problem, that is for the case of argon atom we will check. So, okay, so find the translational partition function of argon gas at 300 Kelvin in a 500 cc container. The given quantities on the mass is the 39, so it's given us 6.636 into 10 to the power minus 26 kg. KBT is mentioned as 4.14 into 10 to the power minus 21 joule. H is the Planck constant, that you know, 6.626 into 10 to the minus 34 joule. Okay, so now so similar way, so first thing the M is given, V is given. The first thing that we need to calculate is the lambda, right? So lambda is h by root 2 pi m kBt. Okay, so h is 6.626 into 10 to the power minus 34, so whole thing divided by 2 pi into 6.636 into 10 to the power minus 26 into 4.14 into 10 to the power minus 21. Okay, So now if you substitute, if you done the calculation, it will give you roughly 3.79 into 10 to the power minus 11 meter. Okay, this is the value of lambda, the thermal wavelength. Now the next things are very easy. So V we know is the 500 centimeter cube. Cc, so you have to convert into meters. It will become 5 into 10 to the power minus 4 meter, right? Meter cube, sorry. Now from here, Q is basically V into lambda cube. So V is 5 into 10 to the power minus 4 divided by lambda cube, 3.79 into 10 to the power minus 11 whole cube. So it will give you roughly around 9.21 into 10 to the power minus 23. So this is the value of Q, the partition function Q. Okay. So this is how the translational partition function you can calculate for this system, for 3D, whether it's a 3D system or 2D system. So things that you need to know is the thermal wavelength of that system particular. So for the thermal system, you know the mass of the particle and the temperature of the particle, and also you need the volume where the container is. If you can calculate these three quantities, you can easily calculate the partition function for the single particle. So that's it. So this is for today's class. So if you have any doubt, you can ask, or otherwise I will stop the class. Then